The rapid advancement in compact mobile electronic and telecommunication devices have caused serious electromagnetic interference issues such as malfunctioning of devices, data loss, or data misinterpretation due to strong electromagnetic induction effect in a close proximity. These highly integrated devices demand EMI shielding materials with lightweight, easy processability, and minimal thickness, along with the improved shielding efficiency. Generally, efficient EMI shielding materials require high electrical conductivity. However, the most commonly used conducting and non-magnetic shielding materials, such as metals and carbon-based nanomaterials, hardly meet these requirements. In 2016, Professor Chongmin Ko in Kist and Professor Yuri Gogochi in Drexel University reported in Science that Ti3C2 Maxine and its polymeric composites showed an outstanding EMI shielding effectiveness of 92 decibels at very thin thickness of 45 micrometers in X-band frequency range, indicating exceptional promise for lightweight EMI shielding applications. This shielding performance was mainly due to the high electrical conductivity of around 4,500 Siemens per centimeter, abundant surface terminations, and the laminate architecture of Ti3C2 Maxine films. This year, collaborative research team of Kist, Drexel University and KU Kist Graduate School of Korea University reported another interesting EMI shielding material. Transition metal carbonitride, Ti3CN Maxine, which has a very similar structure to Ti3C2, with the nitrogen atoms randomly substituting carbon atoms and structurally packed in a hexagonal structure with titanium atom layers. A 40 micrometer thick Ti3CN Maxine film showed an extraordinary EMI shielding performance of 116 decibels due to anomalously high absorption of electromagnetic waves in the layered structure, which is much larger than the 93 decibels measured for a annealed Ti3C2 film of comparable thickness. Surprisingly, Ti3CN Maxine outperforms all other shielding materials with similar thickness, studied to date, including copper metal film, which has several orders of magnitude higher conductivity. The extraordinary EMI shielding performance is due to the anomalously strong absorption property of the layered Ti3CN films. The Ti3CN films have a compacted laminate structure, which converts into a metamaterial-like porous laminate structure after mild heat treatment. Incident electromagnetic waves are strongly absorbed in this porous structure, not only by strong internal reflections from multiple interfaces, but also by the metastructure effect. Designed porous structure with improved effective permeability and permittivity strongly attenuates the energy of electromagnetic waves by ohmic, eddy current, and polarization losses. Therefore, the metamaterial-like structure gave 116 decibels of EMI shielding effectiveness at a 40 micrometer thickness, which is the highest value ever reported for a synthetic material. This high absorption property of Ti3CN Maxine will allow electronic devices to operate without EMI disturbance in compact and smart 5G electronics and communications.
My group at Drexel University explores two-dimensional carbides and nitrides of transition metal, Maxines. Titanium carbonitride has demonstrated a very unusual interaction with electromagnetic radiation. This is a solid solution Maxine where carbon and nitrogen atoms are mixed together. And this finding offers exciting opportunities for further discovery and exploration of carbonitride MXenes with other transition metals. We're very excited about it.
Rapid advancement in highly integrated mobile electronics and communication device requires lightweight EMI shielding materials with improved absorption property. However, commonly used materials such as metals and carbon-based materials do not meet the requirements. In this work, we report extraordinary EMI shielding property of titanium carbonitride Ti3CN MXene and their unusual absorption shielding mechanism. In general, the EMI shielding technology is based on metallic materials because electrical conductivity is the main parameter that determines EMI shielding property. However, metal-based shielding materials do not meet the requirements for highly integrated electronics such as lightweight, low cost, and flexible printing processability. In addition, metal-based shielding materials generate undesirable secondary electromagnetic pollution due to their strong reflection property. In this work, we developed a new types of shielding material, Ti3CN MXene, having an excellent EMI shielding performance, and we also try to understand their anomalous absorption shielding mechanism. In 2016, our group published in Science one interesting paper on Ti3C2 MXene shielding materials having a very high EMI shielding properties. However, still there was a strong need for further improvement in absorption property of MXene material. 2 years ago, luckily, we found the newly developed Ti3CN MXene reveals excellent absorption shielding property. However, we spent more than a year cross-checking the reproducibility of the data and 1 more year understand shielding mechanism. During this study, we can expand our knowledge and understanding on this Ti3CN material. Now we understand that abnormal absorption of Ti3CN is due to unique laminate structure as well as the formation of a metamaterial like porous structure. Ti3CN MXene can be used as the lightweight EMI shielding and absorbing materials in highly integrated mobile and smart electronics and communications. It can be used as the EMP shielding and stealth materials in military for national security. MXene is not natural but man-made artificially. For successful commercialization, efficient supply chain of substance from the synthesis of raw materials and intermediate to the final device should be established. In the early stages, it is risky for the company, therefore, comprehensive government support is very important and urgently required.